right from the beginning. And we can just put in our notes that this is SN1 reactions. So we're going to do a reaction first, since you've already seen some preview of this in a pre-lecture video. We'll just get started right away with it, and then we'll backtrack a little bit, and we'll go through the individual steps, components, concerns, substrate, nucleophile, leaving group, solvent type issues that we did previously. So this particular reaction, SN1 reaction, will typically be set up, and it'll look something like this. This is one of the very, very typical ways that this is written up. And in this particular diagram, we have a substrate, obviously, a leaving group you guys can identify right away. And then we can identify this as a solvent. It's usually under the arrows. And oftentimes, the reagent won't actually be listed if the solvent is playing the role as both solvent and reagent. So we could obviously write water here, but this means that there's excess of water. There's ample amounts of water, no problem. When this particular reaction is run, I'm just going to draw right from the beginning the products we get, and hopefully you could anticipate these as well, because I gave some examples like this in our pre-lecture video. You can think a little bit about how this happened if you want. We will do the mechanism momentarily, but I want you to come up with maybe 2 or 3 observations that you see in looking at this reaction, why it's not an SN2 reaction, or why it's unlikely to be an SN2 reaction. Just throw those in the comments. Just when one comes to mind, you see something, put it in the comments, right? There's at least 3 good observations when we look at this overall scheme. If we were thinking SN2 from our work prior this week, we look at this and we say, there's no way this is SN2. Come up with 3 observations that you see here. First one is racemization. Great, thanks for that, Drake. Some other people chime in too. The product doesn't have inversion of stereochemistry. This is called racemization of stereochemistry, or scrambling of stereochemistry, where we have some retention. Retention just means it's the same, and some inversion. If it was SN2, we'd have 100% inversion from here to here. So the stereochemical outcome is 100% good clue. So let's call this racemization. I love it. This is reason number 1. Number 2, tertiary substrate. We'll call that reason number 2. 100%, this is SN2, impossible or even forbidden. And again, it doesn't look at it like you could just push water here. It looks like on paper it should work. But if you build this with a model kit, you'll see how difficult it is to get at that little nub of a sigma star orbital that's hiding right here. It's surrounded by groups. Great. Yep, Swati, great answer. There's no inversion of stereochemistry, just like Drake was saying. Technically, half of it inverts and half of it is retained, but the mixing of stereochemistry is how we describe that in slightly higher technical words. So half of it inverts, half of it's retained, but the fact that we don't have 100% control, right? And there's one third thing, if we look at this, the leaving group's good, so that's not it. The third and final thing is a little bit more subtle. What about the solvent in this molecule, or solvent in this reaction? The solvent's actually serving the role as nucleophile, but basically if you take this and dump it in a huge amount of water, this isn't a forbidden solvent for SN2, but this is a very slow solvent for SN2. Let's call this reason number 3, because it's polar, but it's protic, and that's the key bit here. That protic solvents tend to slow down these particular reactions. So great work. I really appreciate your feedback. I'm going to try and do this a little bit more. I'm sure it'll wake things up a little bit for us. But let's actually practice the mechanism now and see how this happens. We'll go this direction on the sheet of paper. If your paper notes are a little different, just redraw it. But the mechanism for this reaction we've seen, we have to practice now. Leaving group leaves first, and we make a carbocation. And that's 100% why tertiary substrates are the best for this reaction, because we make a tertiary carbocation. This leads to the issue that Drake and Swati were raising here for us, that we get this carbocation and it's perfectly flat now, and the incoming water molecule can come in from both the top, or we could imagine it coming in from the bottom. I don't like drawing two arrows on the same particular molecule because that mechanistically doesn't make much sense. So let's just do it if we're going to show top and bottom. We could just show one by top, right? Let's just imagine this comes in at the top, this way down. This methyl group will get pushed down, okay? So if this comes in from the top, we'll draw water from the top, and it doesn't get to the alcohol directly, just drawing what that one arrow means. And what the one arrow means is we're going to make a new oxygen-carbon bond. And so we'll get to this type of species here. And I'm showing this coming in from the top. And to get to the final alcohol product, this is highly acidic, right? And we could show water doing an acid-base reaction here. We could show I- doing an acid-base reaction here. But I'm just going to say minus an acidic proton. So we're going to subtract an acidic proton here. In doing so, we'll get to one half of the possible products. This would be from the top, right? And then we could also write from the bottom here. If water came in from the bottom, we make an oxonium that would have a methyl group up, and the oxonium would be down. If we took off the acidic proton, we'd get to this other diastereomer here, or let's just worry about this chiral center. We'd have both of these, and it makes it roughly 50-50 mix of these two things, because the carbocation has 50% p orbital up, 50% p orbital down, and water is surrounding this. It comes in from both of them. So this is kind of a complex introduction, or first slide here, but already you were thinking ahead, thinking about this, and I think the pre-lecture video was crafted in such a way that you could digest some of what we've just done. Okay, so great so far. Let's continue now. We're going to back it up and go to the summation of this reaction. We'll do a simpler substrate, and we're going to go through all the criteria, codify them in our notes, talking about the nature of substrate, solvent, nucleophile, leaving group, and see what things are the same, what things differ. Already, the mechanism is very different. SN1 reaction. Bond breaking of leaving group happens first. And you have to show it that way. You have to show the leaving group leave first. If you actually use a SN2 mechanism when you're trying to explain to me that a SN1 process is happening, if you show a nucleophile attacking tertiary substrate, right away you're off to a bad start. So when we look at a reaction, we'll make a judgment. Do you think it's SN2? If so, all your hard work on SN2, draw the SN2 mechanism. But if you think it's SN1, and this will be usually for a tertiary substrate, show that leaving group break first, right? And second, bond formation with nucleophile happens. So they happen as two separate steps, and you have to show them as two separate steps. Otherwise, logically, it's wrong. Okay? So let's just take a simpler example for our notes here. We'll take T-butyl bromide, this particular compound, and we're going to react it with water. We're going to react it in water, but we're going to use water as our solvent, and nucleophile would be the same if we just wrote it as this. So these two things mean the same thing. There's lots of water, but just by drawing it here, and trying to emphasize the point, this you should think of as solvent, this you should think of as nucleophile, this you should think of as substrate, this you should think of as leaving group, and again, this bond breaks. Make a tertiary carbocation. For this particular example, there's no stereochemistry that we have to think about, and this is surrounded by water. Water adds to it. And we're going to make that oxonium again. This time we'll actually practice the acid-base reaction. So we get to this oxonium ion, and we know we're working slowly towards an alcohol. From this oxonium ion, it's very acidic. You could use Br-, or you could use water. Either one is okay, and you can use these particular compounds simply to do an acid-base reaction. It pulls off the acidic proton, allows us to get to our final neutral alcohol product. So the substitution that's taken place here, very easy to understand. Bromine's been substituted for an OH group. We did this with SN2 reactions. We would have a much better substrate, less bulky, and we could use sodium hydroxide, and that could come in and kick out bromine. But can't happen here because nucleophiles simply cannot find their way to the backside. So instead, if we heat this, bond can break first, then water can add. So, the SN1 reaction, we talked about that bond breaking happens first, then bond formation happens. We're going to find out that the nucleophile doesn't matter. We'll see what this means momentarily, but one thing, that the type of nucleophile we use actually isn't as important, or isn't important as all in the SN1 reaction as it was in the SN2 reaction. Let's think back to yesterday. We actually had some discussion about water as a nucleophile. Oxygen's electronegative, so this is a very, very poor nucleophile. When we were doing SN2 reactions, if we wanted to make this a better nucleophile, we could actually use the conjugate base form, and then hydroxide became a decent nucleophile. But water is really, really poor nucleophile. It doesn't react in SN2 reactions, but here it's reacting. And we're going to come to find that the nucleophile doesn't matter because the carbocation doesn't discriminate. It'll take any electrons that come its way. We know that there's a scrambling of stereochemistry. You know that from the last slide. Let's reiterate it right here. And the rate of this particular reaction is equal to a rate constant times the concentration of the substrate. This particular reaction is unimolecular, and in the rate term, the nucleophile, start over. Scrambling of stereochemistry. The rate for this particular reaction is a function of a rate constant times only the concentration of the substrate. For the SN2 reaction, the nucleophile had a term here, and that was a bimolecular reaction, and the nucleophile matters in the SN2 reaction. Not only what type it is, but also its concentration. In this particular reaction, the nucleophile doesn't matter at all. It's completely missing from the rate equation, and this is going to have a consequence that we don't have to think about nucleophiles in this particular type of reaction anymore. They're all going to be equal. So as soon as we start down the line of thinking of SN1, we'll have an advantage now that all nucleophiles are created equal. I'll reiterate this momentarily. Let's just put to writing that the nature of the substrate is important. You already know this, you probably already know what it is, but I think it's important to write these things into our notes. We have tertiary, secondary, primary, methyl. There's other types of substrates we can have here, but tertiary is the best. Secondary is okay. Primary is not good at all. Methyl's impossible because these all lead to carbocation intermediates. So this follows the trend 100%. We'll contrast the SN2 and SN1 trend at the end, and we'll see how we can use it to our advantage. But first thing to note, exact opposite of SN2 trend, right? The exact opposite. It goes in the exact opposite direction. If we take a more simple example, we're going to do one more simple example using water and a chiral substrate, just to make sure in our notes there's at least one more instance where we illustrate the phenomenon of scrambling of stereochemistry. We'll do it explicitly using a chiral center this time. Let's take Let's take this tetrasubstituted carbon here. It's chiral. Chirality at this particular center is R, and we have a methyl group, an ethyl group, a propyl group, and chlorine attached to it, so we could easily calculate the stereochemistry here. And typical reaction, again, when we do a SN1 reaction, we're going to see time and time again, we're going to have something written like this. This would be like our solvent. It's also going to play the role as the nucleophile, but if we leave it out, then we know we have tons of this and nothing else, and so something's going to happen. So we could write it 2 times, write it 1 time, really doesn't matter. But this will mean the same as this in essence, because this just means there's a lot. Okay, so you might see it both ways. In the sign problems, you might see it both ways. And this leads to, as we do this reaction, tertiary, no SN2 reaction. Water, it's a poor solvent for SN2 reaction. Water, it's a poor nucleophile for SN2 reaction. But if we have a little bit of heat, this can break, and it leads to carbocation intermediate. This is sp2 hybridized. And so, even though these are wedges and dashes here, this is flat this way. Right? This is not tetrahedral, it's actually flat and tilted on its side. We just can't draw these groups perfectly overlapping with one another. So this is a planar molecule about all these carbons here. This one, this one, this one, and this one are all planar. They're all in the same flat plane. And there's these 2 lobes. It's sp2 hybridized. This here is an empty p orbital. And water can come in from either the right or the left. And so ultimately, as water enters from right or left, right, I'm not going to draw it. I've drawn a few little too many arrows here. But if water comes in from the left, well, let's do the right first. If water comes in from the right, we'll have an oxonium ion, and it's deprotonated. We'll make an alcohol where water came in from the right, and these groups will all get pushed to the left to make room for it. So that would look something, that'll look something like this. Ultimately, we'll have this group here. The methyl group will get pushed to the left. The ethyl group will get pushed to the left. And the propyl group will get pushed to the left. Right. And this stereocenter, if we care to calculate it, will be S. And if we came in from the left side, did our deprotonation step of the oxonium ion, this is the chirality of the molecule that we would have, right? So we're coming in from the right-hand side, we make this one, we come in from the left-hand side, these groups get pushed that way, and in this particular example, this one here would have, let's see, R stereochemistry, okay? And this happens about 50-50 times. So using this particular example, just using an explicit chiral center like this, lets us really put in to our notes the nature of the stereochemical racemization. So substrate does matter. Tertiary is the best. And yep, I'll be really careful, a little bit more careful about this. Let me lift up the camera just a little bit. I have slightly different paper